So, ladies and gentlemen, welcome to this latest teaching session in the course on technology and the future of medicine. Today, Dr. Zaiane is doing the main show, so I just have a short warm-up here. So, this Promise and Perils of AI Part 1. The objectives of the AI lectures to introduce you to the basic elements of AI, introduce you to the concept of influence of AI and the exponential future, and to provide you concrete examples of AI in everyday life and in medicine. AI may seem like just another subject, but it is likely the most important area addressed in this course. And if you think of existential risk, the things that could cause the end of the human race, in short term it would be nuclear war, but if we survive the next 10 to 15 years, then AI probably represents the greatest long-term existential risk. And I suppose one of the purposes of the course is to kind of empower you guys a little bit to be able to shape the future to make it more likely to have a positive outcome. So AI is very important to the singularity, but that does not mean that all AI researchers believe in the singularity or have the same beliefs. And so, for instance, some don't believe in it at all, some believe it'll occur sooner or later, and so on. So the idea of 2029 machines as smart as individual humans, 2045 as smart as the whole human race, so they may hold a general belief that those things will occur, but in a very different time frame. And something happened yesterday that was sort of interesting. There was an article saying that Moore's law is dead, that it's done, but I don't think that's quite true, but it will presumably wind down sometime in the next few years. The prediction is 2025. So what does it mean then? I show you all these curves of Moore's law and tell you that it's so important. So if it's winding down in 2025, is all exponential tech advance going to wind down at the same time? I don't think so. I don't think the one depends upon the other. The Moore's law curve is just the kind of metaphor for a lot of other things that are changing at a very rapid rate. So you can read about AI in books, but I think experiencing something like the Sony Aibo robotic dog gives you much better kind of feeling for how it actually works. The dog's last production run was in 2005, October 2005, and it's actually pretty cool when you listen to what the dog says. He never insults you. He offers you the kinds of things you'd want from any friend. He tells you he loves you. He asks you if you're tired at the end of the day. All that kind of thing. He apologizes. You know, things like that. And so you can imagine if Sony had continued all throughout this period, where the robotic dog would be now. And there will be a new Sony Aibo robotic dog in 2019, so they are going to start up the series again. So these are the various parts and sensors that the dog has. And the elbows are really quite important, because from a computing science point of view, the use of these dogs in robo-soccer was very big. And that didn't work very well with the dogs walking like that, but walking on their elbows worked really, really well for robo-soccer. So these are dogs playing robo-soccer. And Sony Aibo robotic dog was popular with AI researchers in Canada, but not with ordinary Canadians. So I had great difficulty obtaining the new model. So this is how it works. It can automatically find the charging station and, in theory, keep going forever. It's much less interest in the AIBO in Canada than in the US. So in 2003 and 2004, the only way I could get the new model, this guy, was to fly to a hotel in the US, wait till my package arrived, and then fly back. Because Sony has these buying around rules where you cannot, from Canada, buy from Sony US, because in theory they have the same products as Sony Canada. So you have to physically be in the US to get something from Sony US. They are adult toys. A child playing with one of these pulls off the ears and tail within about 30 seconds. It looks really stupid without the ears and tail. So it is really for you. The primary market was affluent young women, particularly in Asia and Europe. And even the men who bought them usually bought them for the young woman in their lives, and so it was thought to bring out maternal, nurturing feelings. And Asia will probably lead the way in the development of robots for consumers. Most government investment in robotics in North America is military robots, clamshell robots pick up injured soldiers in the field and that kind of thing, whereas in Asia, it's robots to care for the elderly and do household tasks. So most consumer developments in this area will probably come from Asia. Blade Runner, the classic 1982 movie, which probably all of you should see sometime.
Not the new one, the old one.
No, the original one is a part of everyone's consciousness in this area, but it's important to remember that the replicants in that movie are the product of genetic engineering. They are not silicon-based. They're biological creatures, so it's completely different from most robots that you would think about. So, for instance, the movie AI has a silicon-based artificial intelligence, which is most of what we think about in this area. Okay, so that's my warm-up, and now Dr. Zaiane will continue. So,
Okay, I'll try to lead up my view of this. So, I've been giving this talk for many years now.
yes?
I've been participating in this course for many years. And each time I add something, but for somebody who saw it again and again, it was kind of boring. And last year, was it last time anyways I gave it,
Yeah.
I did a radical change, and Dr. Solis liked it. He said, wow, this is the best one so far. So I decided to, start again. I decided to change it again.
All right.
Just to please
Cool.
you. Cool. I gave a talk recently about AI and machine learning at a conference in neurology in Germany in June. It was epidemiology and neurology. And I started the warm-up, like you call it, with well, about a case. I mean, I was talking about the case of the Ebola virus. So the Ebola virus, because this was a conference on virology, it's one of these filoviruses that are very deadly, extremely deadly. Was identified in the 70s, and we still don't have a cure. When people get Ebola, It's, the probability to die is extremely high, and it passes from one person to the other very quickly. So in 2014, not a long time ago, there was a significant outbreak in Western Africa. And at the beginning, they had no idea it was Ebola. Actually, they thought it was cholera because they identified the bacteria and they said, okay, that's cholera. We didn't think it's a virus. It's only months later, so it started in around December of 2013. It's only in March of 2014 that the World Health Organization said, yes, that's Ebola. Now we have to change completely the strategy. But by then, you can imagine, I mean, it was a big deal. So here's the countries that were touched. There was Guinea, Sierra Leone, and Liberia. That was a big deal in this part of the world, but it contaminated other people because people travel. And when you look at this map, say, gee, that's a small part of Africa. Who cares? Like many North Africans would say, North Americans. But you can see these are big countries. This is compared to some countries in Europe. But what you have to keep in mind, not only these are humans, dying, many people are dying, but these people, the reason why it was actually moving from Guinea, started in Guinea and went to Liberia and Sierra Leone, because people were sick. They didn't know why they were sick, and they went to these hospitals across the border. And then the hospital was contaminated. And many people who died, actually, they're nurses and doctors from these hospitals. But what you have to keep in mind is from these places in the world, look where they touch. They travel to all these places. So very quickly, something like Ebola can be a global risk. We don't have a cure, and people die quickly. So it's very serious. So when this happened, and now they identified it's Ebola, the first thing to do is to identify patient 0. Where did it start? Okay. And typically what they do this tree, they do it manually to start to see, okay, who contacted who moved to who, and all that stuff, until they reach the origin. But instead of doing manually, because by then, 4 months passed, you have a lot of people contaminated, they used machine learning techniques. In this particular case, actually, they used what we call social network analysis. They build a social contact graph, and they analyzed it with machines, and that's how they reached, with these models that they built, they reached the patient 0. Patient 0 was Emile, a small boy, 2-year-old boy in Guinea, who died from it. So he was already dead, but we identified the place, family was already dead, and we tried to identify where did this child get Ebola. What we know is that some species of fruit-eating bats are what we call Ebola reservoir. It means that they carry the virus, but they're not affected by it. And then they can pass it to humans and primates and stuff like that. But there was no fruit-eating bats in that village. So where's it coming from? They heard the story, the World Health Organization investigators that went there, they heard that there was a tree, the tree burned by then, where there were bats. The bats were gone because the tree was burned. And they were not fruit-eating bats. They were insect-eating bats. So now they need to investigate what was going on. It's not these bats, but these bats. What does that mean? So they used machine learning, again, to identify the potential Ebola reservoirs, other animals. So they took characteristics of these animals that they know are Ebola reservoirs, and they took about 57 variables, and they built these machine learning models, actually decision trees in this particular case. If we have time, we'll talk about decision trees. not today, but in the other lectures. They build different decision trees, so they discriminate between the two different classes, basically, and they can calculate the accuracy of these trees, and then they adjust them, they build all the trees, adjust them, build up, so this one was 64% accurate, 71% accurate, they continue to do that until they reach an accuracy that is acceptable. In this particular case, it's a paper, okay, that talks about this method. 87% was acceptable, and that tells them the characteristics of potential reservoir. And then they map this on where are these species, and they realize, oh my gosh, this is what we thought. This is actually the real map of the world of where potential Ebola outbreaks could start. And interestingly, they see that there's a hotspot in Thailand, so Thailand, Malaysia, Vietnam, Laos, that area. Yet we never hear of outbreaks there. It's a hotspot, but we don't have outbreaks. The outbreaks are in Africa, so why? So now you can see that machine learning is not just used for hypothesis testing, but it's also generating new hypotheses. And this is important because now they can check and monitor these areas before an outbreak happens. And if something happens, they can put it high risk Ebola, because now we know that there are reservoirs. I said that Ebola is not a curable disease, but people obviously are working on this to try to cure it. There's actually currently a vaccine that is being tested, but not a cure. But they have identified some pharmaceutical ingredients that have some potential anti-Ebola virus activity in vitro. So that's interesting. But we have millions of these commercially available molecules. Are we checking them all? That's too many. So again, this is another paper. They talk about how they use machine learning to reduce that search space. And what happens is that this machine learning technique identified some of these commercially available molecules, and then they tested them. They ranked them and tested some of them that you didn't even know, and we can see that some of them have huge drug potency against Ebola virus, so it's very successful. So this is the warm-up, just to tell you that, yeah, machine learning is quite useful in medicine, has a lot of potential. But I didn't tell you what is this machine learning. I didn't tell you what is AI. So I'll try to define a little bit what AI is, tell you about what is machine learning, and then we'll talk about why now. Because actually this technology is not new. We started hearing about it, and people are starting to be excited about machine learning and AI, and they try to apply it in fields that we didn't think about before, or didn't consider before. But that technology existed for a long time. So why is it coming back now on force? Then I'll talk about precision health, and I'll show you some examples. If we have the time, otherwise I'll continue the examples on Thursday. Okay. Any questions? You can interrupt me anytime. I don't want to be the only one speaking. Questions?
Just quick, can you keep the light a bit? It's just glaring really badly.
It's also in my
Sorry.
eye. Is that okay for the camera?
Yep.
Yeah, maybe it's you.
Thanks.
But that wasn't a question. Well, it was a question. The question could be.
What was an important question, but not the kind you were looking for.
Thank you.
I was
You
going
better
to
ask
ask,
that question in the beginning than at the end, because it's useless. Yes?
what made you interested in AI and machine learning?
Whoa, that's a very good question, but I will leave it till the end. Because it's a long answer. Okay, so what is AI? This is a slide borrowed from NVIDIA. As I said, AI is an old technology. It has been around for a long time. The term was coined in 1956 when they organized the first conference, symposium on artificial intelligence. They invited people who were already considering these thinking machines. And in those early days, they were very naive. They thought, okay, we have these machines that we were using in the Second World War to decipher code, to calculate trajectories of missiles and stuff like that. Now that the war is over, how can we use these machines for the social good? And many philosophers and scientists working on these machines have said, well, actually, we can make them think like humans do. How? Well, the human activity, the intelligent human activity, can be divided into small pieces, and we can code every single small piece separately, put them all together, and voila, you can create a machine that thinks. That was a very naive idea about what human intelligence is. We still don't know how this brain functions today. We have hypotheses. But nevertheless, they build amazing things. So there was a hype, like there is now, about AI. There's a hyper-optimism. Everybody thought, well, yeah, that's it. We will build machines, to the point that, remember, after the Second World War, there was this Cold War between the East and the West. So both wanted to have this thinking machine, of course. There was a lot of investment for research. There was a lot of, a very high expectation. We will do it, and now this machine will think for us. But very quickly there was disillusionment. They didn't reach that goal that they set for themselves. So the solutions that were done at that time, in the first 3 decades, were basically computers mimicking human intelligence. They were mimicking how we were doing things, whether it's playing chess or playing this or whatever. The games actually were used as a demonstration of intelligent programs, because you need to be intelligent to play chess or intelligent. That's what we think. You need to be intelligent to play chess, checkers, and cards, and all sorts of things. It's in the 80s that we started seeing the rise of a technology within the realm of AI that we call machine learning. Machine learning is about teaching a machine to learn. And then there were, so this, in this case, computers are learning without being explicitly programmed for a particular task. They learn that task. So we code them just to learn, and then they can do that task. And I'll explain that to you later. So this brought back hope. Remember, there was disillusionment. And now this brought back hope, because there were many applications where we recorded success. Okay. There was disruption in many fields with this technology. After 2010, there's a new technology that is in the realm of machine learning that is called deep learning. And deep learning has changed everything. Have you heard of deep learning? One person heard of deep learning? Okay, so the media is using it. You can even see it in jokes, in cartoons, and in movies. But nobody knows what it is. So you will know by the end of the day. Okay? So deep learning, it's learning, but it's using artificial neural networks. And again, artificial neural networks is not a new technology. It existed since the 50s. So I'll give you the big picture of how things are, because now people are confusing deep learning and machine learning and AI, and it's becoming synonymous. Actually, they're one inside the other. So this is the field of computer science. In the field of computer science, you have many subfields. One of them is artificial intelligence. I made it into a big circle because I'm going to zoom in, but it's the same level of importance as many other subfields like networking, high-performance computing, software engineering, graphics, database management systems, security and encryption, algorithms, human-computer interaction, and so forth. Like in medicine, you can say, well, there's nephrology, there's pathology, there's radiology, there's pediatrics. There are different subfields, and they work together. I mean, radiology sits across many fields. Okay? You have the same thing in computer science. Now, if I zoom in within AI, artificial intelligence, you have many subfields as well. One of them is machine learning. But you have also planning, you have knowledge representation, you have reasoning, computer vision, natural language processing, and so forth. All their subfields within AI. So machine learning is a subfield of AI. Within machine learning, I have many subfields too. We have what we call supervised learning. We have unsupervised learning, we have reinforcement learning, and other paradigms as well. If I go and look at supervised learning, that's where I'll see deep learning and other techniques as well. So deep learning is basically within supervised learning, which is within machine learning, which is within AI, which is going to be responsible. Okay? They're not equivalent. It's one side the other. I hope you have a better idea about these terms. You still don't know what they are. So what is this artificial intelligence? There's an artificial brain here with connections. I like that drawing. I didn't do it myself. I probably don't know why. So artificial intelligence, you read the articles, and they say, well, AI market will be worth $60 billion by 2025. So, well, AI must be something important. There's a lot of money involved. Okay? And you have many of those articles, journalists write this stuff without telling you what AI is. So now it's becoming part of the jargon, but we haven't defined that term. You can find articles that say, the one who dominates AI will rule the world. This is actually a quote. Do you know who said that? Vladimir Putin. So when Vladimir Putin says that, wow, AI must be very, very important. This is not only an expensive thing, but it's also very powerful. Okay. So what is this AI? Well, we read the magazines. They'll tell us what AI is, and we'll get things like that. I have no idea what it is. So where we get our definitions? Movies. Okay, Blade Runner. All sorts of movies. Unfortunately, those movies, they do not portray the reality. Science fiction. And they give you often a very pessimistic view of what is AI. You know, very often they'll show the machines against us, the humans, so them against us. And that's definitely the wrong image that I want you to have. As Dr. Solis said at the beginning, we're teaching this course so that you, the next generation, will make sure that we have a better world, that we won't have this them against us. The machine versus humans or AI is now an existential threat, and many people have said that, and not any people. There are some very important people who have said that. If you want to know what AI is, your phone. That's the level of AI that we have today. Okay? Not what you see in movies. But we'll see very interesting examples later on. Again, I haven't defined what AI is. So what is artificial intelligence? Not from the movies, forget the movies. If I go back to one of the pioneers in the field, one who was one of the co-organizers of this first conference in 1956, Marvin Minsky. He's the founder of the first AI lab in the world at MIT, research lab. He says artificial intelligence is the science of making machines do things that would require intelligence if they were done by men, by humans. So it doesn't mean that they are intelligent, but mimicking is still fits in this definition. So artificial intelligence is a discipline, it's a science. They try to get machines to behave intelligently and performing tasks that would normally require human level intelligence. The reality is that this definition is very vague, and many things can fall into this definition, and then when we get used to it, then we take it for granted. So actually AI is a moving target, it's changing. Okay? If I take the example of a typewriter. Have you ever seen a typewriter? Okay. I took my kids to a garage sale once, and there was a typewriter. I asked them, what is it? And they thought it was a computer, a very old computer. Well, the new generation hasn't seen these typewriters. So I bought that typewriter, and now they play with it at home. What they used to play, they don't play with it anymore. But anyways, go back to that time. And imagine how you type a text. So when you were typing a text, character by character, you reach the end of the line, there's a lever, you push the whole thing, and you type again, push the lever. So if you wanted, for example, to justify a text, you wanted your text to be justified on the right, or justified left and right, and aligned, that was tedious. Before you start typing the line, I mean, there were expert secretaries who knew how to do that. They go and count the characters, say how many spaces do I have in each, between the words, how many words I have in that line, and it was a complicated thing. Okay, you understand that? Now we have word processors. When the first word processors came out, you put the text in, press a button, boom, it was done. People would say, wow, that is amazing, very intelligent. It makes sense, doesn't it? It was mind-boggling. How can you do that? And you press another button, left justify, another button, right justify. That was amazing. Today, who cares? We're so used to it. It's normal. That's what I mean by a moving target. It's not intelligent, it's actually dumb to do that. It's so easy. And many things we think are smart today, tomorrow we'll take it for granted as well. It's not AI anymore. Okay. For me, the definition of AI, I think that artificial intelligence is actually a tool. It's an enhancement to our own creativity. For me, it's like a hammer. I couldn't press the nail with my thumb, I'll injure myself. I invented the hammer, not me, but the humans, so that we can extend our capabilities. It doesn't mean that that hammer is better than me. I built it. AI is the same thing. I'm building AI to help me do things that normally would take me a long time to do, or they're tedious or repetitive and things like that. Okay, just an extension of me, and I become better with the AI. That's the perspective I want to see. I don't want to see them against us. Dr. Solis also mentioned in his introduction the term data mining. Have you heard the term before? Data mining? Yeah? Do you know what it is? Can you define data mining? So it's like AI. You know AI, you heard it, you may even use the term, but you don't necessarily know what it is. Okay. You have some assumptions. So I'll try to define what data mining is, and these two are actually cousins. Okay? AI and data mining. So data mining is actually a process of many steps. It's a repetitive process. The goal is to discover patterns in data. Patterns that are basically knowledge, which was previously unknown. That's why we call it discovery. And it's typically hiding in large collections of data. The goal is to find patterns that are actionable, that I can use for decision making. Okay? So the analysis and intelligent interpretation of this large data, and in order to find these patterns that are actionable, which is knowledge, for either human decision making, I see these patterns, now I know what to do, or is actually input for another program. Okay? An automatic decision making. So it can be a program that uses these patterns and exploit these patterns. In reality, data mining is actually at the confluence of many fields. You have statistics, you have information retrieval, high performance computing, visualization, because you need to be able to interpret the data, database systems, and also artificial intelligence. So artificial intelligence participates, that's why I'm saying they're cousins. Among them, machine learning. So machine learning is within AI, and it's a fundamental part of data mining. In machine learning also, you try to find patterns that will help you discriminate between one task and the other task. What I do this or I do that later. Okay, so we build the model, and I'll show you that later. Okay. Now the fun part about this lecture, and you will learn something for sure. Why is it now? Why now? AI is coming back, and people are believing that this is the solution. It will help us for many, many different things. There are three factors, three important factors. Can you guess what it is? You know it actually. If you hesitate. First one is data. We are collecting a lot of data, more data than we have ever collected before. Every year, we collect more data than the last 10 years. And every 2 years, actually, what we collected in the last 2 years is more than what we collected in the history of humankind. It's going very fast. It's exponential. The second factor is that computers, so Dr. Solis mentioned Moore's law, computers are becoming amazingly powerful today, more powerful than yesterday. So these computers can handle the amazing amount of data before we couldn't. And in addition, there's a third factor. We have new algorithms that can run on these amazing computers and couldn't run before, and they can exploit this data. I'll give you a better picture of what's going on, and it's actually shocking how fast things are changing. Where's this data coming from? If I just focus on the data, I'll be focused on each one of those. This is from 2013. They're just telling us how many emails are sent every minute. This is what happens on the internet every minute. How many emails are sent? How many megabytes of gigabytes or terabytes of data is uploaded to YouTube every hour or downloaded from YouTube to be watched every minute? It's mind-boggling. And this is 2013, 5 years ago. It's way more than this. Since this is in the fact of medicine, I'll mention medicine. That's not working here. In healthcare, we also collect a lot of digital data about patients, different procedures we do for drug development, like the Internet of Things. If you go to an ICU, intensive care unit, there are many sensors. They're all collecting data. Okay, that data goes somewhere. Every second, or every millisecond, they're collecting data. You look at the electronic health record. Insurance providers are collecting data. Clinical trials are collecting data. We have the genome data from the social media, etc., etc. We're collecting a lot of data. In 2011, there was a paper that was attempting to measure the amount of digital data collected in the US alone. And they said we're reaching 150 exabytes. So this is a billion bytes. And they said we're reaching the zettabyte. This is 1,000 billion bytes. I mean, it's a big number. What does that mean? So, okay, there's another paper that says, okay, I can visualize it for you. It said if you put that data on CDs and you stack these CDs, you will reach the moon. Okay, they calculated the distance between Earth and the moon and how many CDs they need to put that data, and then how thick is each CD, and you can see that you go. In 2007, actually, we passed the moon. That gives you an idea about how much data we're collecting. Who cares about CDs? Recently, they did the same thing, but with DVDs, and we passed the moon twice. Okay, that shows you how fast we're collecting. Who cares about DVDs? Yes, you have questions.
So what role does AI play in storage of this information?
Oh, we are not talking about the storage in the AI. We're talking about the fact that AI will take advantage of this data, because there are techniques that the more data you give it, the more accurate it gets. Okay, I'll mention that. But the storage, yeah, there are some techniques for, AI techniques exploited in storage, particularly when you need to make sure that the storage is robust. You don't store it in all one place, you store it in many places. And you take an example of social media. You have some people in the Middle East, you have some people in Australia, you have some people in Africa, you have some people in North America. And to serve the people in Africa, they want to have some information that was created in North America. Do I have to store it also in Africa? All of it? And all of it in North America? All of it in Asia? All of it in Europe? To serve everybody quickly? No, so there are techniques that will tell me where to store what, such that I serve the people here fast and the other people fast. And at the same time, I'm actually guaranteeing that if something is deleted, I can still recover it. So there are techniques for AI, AI techniques that are used for storage and distributing the data efficiently so that everybody is served properly. But I'm not going to talk about that here. Here I'm talking about data to show you how much we're collecting to justify why actually it's part of the resurgence of AI, basically, because AI takes advantage of that data. So, why am I talking about DVDs? Who uses DVDs anymore? Okay. So let's visualize something else. I want you to realize how much data we're collecting. If I'm storing everything in DVDs, and the collection of all the data just in healthcare allows me to go to the moon with these DVDs, obviously DVDs is not the right way to store data, because I need a pile bigger than Mount Everest. Okay. I can't afford that. So data is stored in smaller spaces, and if I show you the smallest storage device that you played with is an SD card. This is a micro SD card, the smallest one. In 2005, okay, 13 years ago, the best storage you can have on a micro SD card is 120 megs. Okay? A few years later, we reached 128 gigabytes, not megabytes, so 1,000 times more. In 2016, so 2 years ago, we reached 256 gigabytes. This year, 512 gigabytes. So we doubled. So that means in 13 years, we improved 4,000 times. I can put 4,000 times more information in the same space. That's what you have to think about. No, forget about the DVDs. What about the price? Well, this is a picture taken in 1956, so 6 decades ago. IBM was selling a hard drive to a company that could afford it at that time, $120,000 to buy a 5 meg hard drive. 5 meg hard drive, you can barely put some pictures nowadays. $120,000. This is a picture that I took a few days ago from a famous online retailer, I won't name it. For 64 gigabytes, you can buy it for less than $20, let's say $20. So that means if I take the 64 gigs in 1956, that would have been $1.5 billion. Can you imagine that? It means the improvement in terms of price is 76 million times. Okay? It's mind-boggling. That's why it's free to store. Now, you don't delete anything. When you put it in a hard drive, you don't delete it, just leave it there. It's free to store things. Okay, what about enhancement of computers? Today, You can buy a GPU, you know what a GPU is? It's a graphics card. People buy these graphics cards to play games on the computer. So, among the best graphics card you can buy today to play games is like the Titan X, for example, is $1,000. Okay. $1,000. Many people are buying them just to put on a commodity computer to play games. What a waste of time. But that GPU for $1,000 is equivalent to the Cray 1 that was in the 80s the fastest computer in the world, and it was $10 million. It's the same power. Now for $1,000 you can put it on a computer and play games with it, while this was used to do very serious stuff. This is the progression of the most powerful computers in the world. It's collected by a website called top500.org. And you can see 3 curves here. This is the best computer in the world at that day. This is measured in flops. Flops are floating point operations per second. How many operations you can do per second, that machine can do per second. And you can see that this is logarithmic, so it's not linear. So it's multiplied by 10 each time you go this way. And this is the fastest computer today. These ones, this is the number 500th fastest computer, and this is the sum of all of them. So we'll focus just on this middle one. For many years now, the Chinese had the fastest machine in the world. And every year they have new tests and we have a new machine. And before it was the Americans. This year, for the first time in many years, this came out in June 2018, the Americans have the fastest computer. What is the fastest computer? For a few years back, here in 2016, we were reaching the 100 petaflops. What is Perils? That's a million, billion instructions per second. I mean, it's mind-boggling. Let's go back to the best computer that you know. Again, the cell phone. Okay. Your cell phone, how powerful is that? If I look at the most powerful cell phones that came out recently, you have the iPhone X, which is about 600 gigaflops, and the Samsung S9 is 700 gigaflops. Okay. When do they fit in this graph? They will fit here. So that was in 1997, I believe, yeah, 1997, about 1 teraflop. This computer, the ASCII Red, in the San Diego National Lab in California, that computer, in the 90s, not a long time ago, 20 years ago, okay, was $55 million, the size of a tennis court, and the power required for this machine could power 800 houses. Okay. Now, you have it on your phone. The same power. And you take it for granted. But that machine, how many countries had it? 1. 1. Now everybody has a cell phone. Okay. So now, check here on the desk, I'm going to put that phone. They're equivalent. It's mind-boggling, isn't it? Okay. Let's make it even worse. If I compare the fastest computer on this graph, this year, and the fastest computer in the first one in this graph in 93, when I started my PhD, okay, the difference, and remember this is exponential here, this is the difference, is 206,000 times. 206,000 times faster from 93 to now. And that's why computers now are so fast they can do things in AI that we couldn't dream to do before. So what does it mean 206,000 times faster? I mean, it's very difficult to imagine what it is. So here's an analogy that I'm gonna give you. If when I started my PhD in '93, I was doing one step, that's 1 meter, 1 yard, 1 meter. And if I did the same progress like these machines in those years, my step would be equivalent to what? 26,000 times faster than just one step for 1 meter. That's 26,000 meters, that's 26 kilometers. That means if I did one step in 1993, today my step would allow me to go anywhere. See, that's Edmonton? Yeah, just one step. Almost reach Calgary. Lloydminster, I'm in, almost in Saskatchewan. Can you imagine that? That's exactly what computers did. Okay, the progress. By the way, if I use that analogy for these disks, this is in the case of Banff, so I'll be outside of Banff, it's like 4 kilometers. For this, what is 76 million times one step? That's 76,000 kilometers. That means if you believe that the Earth is round and flat, like some people do, I'm almost doing twice around the world, one step. It is incredible. Yes, in 60 years, but 60 years is less than a lifetime. Okay, so drastic improvement in, increase in the amount of data, incredible improvement in the capabilities of computers, but also we have new algorithms. They're not really new algorithms, they were algorithms that existed before, but we were not able to try them out. They were theoretically doing things, but we couldn't try them. So we made small pieces of them and we tried those, and then we forgot about them, namely neural networks. We couldn't build big networks. Now we can, okay? And that's what we call deep learning, okay? These big networks. So what is a neural network? Basically you have units, neurons, artificial neurons. They're interconnected and they are organized in layers. You have an input layer that gets the information, that's the input. It passes the information to hidden layers. Hypothetically, you have many. And then that information is passed to an output layer and then you can measure it. In the olden days, we didn't have big computers, so we couldn't build big networks. We had just one layer, one hidden layer. Okay? If you zoom in 1 unit here, it's a neuron. It represents an artificial neuron. It gets input with different weights. These are like the dendrites, collecting data from different neurons. And then you have the soma of the cell that will decide, okay, now I got enough information, when do I fire? Boom, I send the message. So there's an activation function here that sends the output to the next layer, and that's the axon of the neuron. So basically simulates a neuron. What we can do today with the amazing computers, we can have many layers. And because we have many layers that are deep, we call it deep learning. And these, to learn, if we have time, I'll talk about how the neural networks learn later on in the next lecture. They iterate over the data. That's their experience. And the more data you give it, the more experience they have. And they learn better. And that's why having a lot of data is very useful for these models. Okay, so today, because now we can build these deep networks, we can try different architectures, and many architectures have been proposed. So we don't just have fully connected, we have some that are connected in an intelligent way that we call convolutional neural network with different components. We have also RNNs or recurrent networks, so one layer passes the information to another, not layer, one network actually passes it to another network and so forth. And learning for sequences, like sequences of words. You have also special memories to remember things from the past, like the LSTMs and guns. One thing that I want to emphasize, because we are here in Canada, because you need to be proud of it, why this survived and now it's actually helping the resurgence of AI. It's because despite the fact that people lost hope in these artificial neural networks, are very small, they were not very successful compared to other methods, there were some people who were stubborn enough to keep on working on this technology and doing fundamental research, even though they didn't have the means, they had the paper and pencil and they worked on it. And these people, when the time came and we have the data, we have the computers, they use their technology and they beat everybody else. These people are namely Jeff Hinton from the University of Toronto and Yasha Benger from the University of Montreal. So Canada is a big player in the world when it comes to deep learning. Of course, there are other people like Jan LeCun, who is now the research director, AI research director at Facebook. Schmidt-Rudolph, who is the inventor of the LSTM, is in Switzerland. Lugano, he's a German, but in Switzerland. But here's what happened. In 2012, there was a competition. Actually, the competition existed before. It's about recognizing what's in the picture. So here are many pictures, tell me which one is about an animal, which one is about a tree, which one is about a house, and so forth. You have millions of these images and you have many categories: plants, animals, devices, food, structure, and so forth. And if you give these images to humans, they make mistakes too. Not everybody's 100% accurate. So typical humans, their accuracy is between 90 and 85%. Okay, so they do 10 to 15% errors. The expert humans, they reach 95% accuracy. Okay, they still do 5% errors because these pictures are not obvious. Okay, the pictures taken, they're not just taking this plant there and taking a perfect picture of it. They're all sorts of images. So humans, we make mistakes. Okay? Computers, 2009, 2010, 2011, this is the competition of previous years. They were reaching 71, 75% accuracy, still far behind. In 2012, unbeknownst to the other participant, there was a team using deep learning and graphics cards, GPUs. And this team, for the first time, was using deep learning. The others were using other kinds of techniques that were popular at that time. Nobody was thinking about deep learning. They jumped to 83%. The year after, 88%, 93%. Now they do better than humans, better than the expert humans. And people at that time said, "Oh, what did you use? How come you jumped that much?" I use deep learning. What's deep learning? The neural network thing? Yes. People were surprised. That team was a team led by Jeff Hinton from Toronto. So Google, of course, hired them, and they tried it on the massive amount of data that Google has, and it worked to identify cats and dogs and things like that, and build the models of to recognize a cat without even telling it what a cat is, and so forth. People were flabbergasted. Wow, this is fantastic. But can it do more than that? Yes, this is for image recognition. Let's try it on speech recognition. This is another very challenging problem. DARPA had a big collection of recordings, people speaking on the phone, and they needed people to transcribe this in text, okay, for different reasons, the surveillance or whatever. And computers for many years, and teams from big companies trying to beat that, and you can see they're flat, flat, flat. They're not improving much for many years. So what is speech? Well, basically it's like an image. You have frequency and amplitude, and so you can look at it like a 2D thing. And they applied, now it's a little bit more complicated now, but in the early days they just applied deep learning as it is, and very quickly started going down, and now it's doing better than humans. Humans also do, in this particular case, 5.5% error rate. This is error rate, so the lower is better. And these machines now are doing better than humans. Yes?
I wonder, do they use, so with these neural networks that's involved in deep learning, do they use the perceptual schemas like humans, such as like statistical learning or translation probabilities, like especially with speech
I will
recognition?
talk about how these work. They're not like what humans do.
Okay, that's
Completely different. We still actually don't know what humans do, how we think. And if you even ask, for example, you go to a particular task, like playing chess, and you ask Garry Kasparov, why did you do this move? It'll help you win 10 moves down the road, but nobody thought about why did you decide to do it that way and not the other way. They would not be able to answer you. We don't know how we think. We use intuition, we use emotions, we use things that we don't have in the computers. We use tricks, we bluff. Computers don't know how to do that. And we don't know how to tell computers to do that. Yeah. Anyways, this is just to show that computers now are beating humans at tasks that definitely need intelligence. But they're not that intelligent, yet they exhibit that intelligence. Here are all the tasks where, well, I mentioned about the object detection and images. So they tried them in machine translation, translating from one language to the other. And indeed, deep learning is helping now translation programs better than before. They're not doing as well as humans yet, but they improve significantly to the point that now you can use your phone, and your phone is using deep learning, and you can translate in, like going to a restaurant, a Chinese restaurant. I don't speak Chinese. I can say the sentence and press a button, and it will repeat it in Chinese. Then it's accurate enough. Other examples. This is for the case of it's image querying. So you have an image, and the program describes what's in the image. It'll tell you there's a person riding a bike. There's an animal or a cat sitting on a chair. There is a kite flying over the waves of the ocean, or whatever, things like that. So this is description. It's not just recognizing this is a cat and this is, it's not just recognition, it's actually explaining what's in the image. It's getting better and better. It's not better than humans, even performance still higher, but we're getting closer. This is for question answering, for text understanding, comprehension, like we do in high school. You give a text and you ask the students to answer questions about comprehension. Well, computers are also getting better and better and getting very close to humans, thanks to deep learning. So what is machine learning? I have to be careful with the time. And I'll stop before we go to precision medicine to give you the chance to ask questions, and maybe I'll talk about precision medicine next time. So what is machine learning? I haven't defined it yet. So machine learning is basically a means given to machines to learn from data by interpreting trends in the data. Remember when I talked about data mining is extracting these trends. So you interpret these trends in the data to adapt to the data. So basically you have experience learning, and that experience helps you predict so that you can adapt to the data. New data coming to you. What is adapting? Adapting to data means you have new data you haven't seen, but you can process it. I'll give you examples. So this is a field inside AI, like I explained before, and deep learning is one technique within machine learning. All these machines all these methods are part of supervised learning, as I showed you in that graph. And supervised learning means that they are supervised. How do you supervise them? You give them some training data. There's data that is annotated, and it learns from that annotation. You help them out first. And give them training data. There are other techniques, and I have it here in the slide. Oh, before I go to the other techniques, I'll show you visually what that means. So visually, you have data that is annotated. That's the training data. I'll go back again. The program goes over it, learns from it, and builds some knowledge, a representation, a model. A model that will discriminate between the different labels. Okay? I put it as a cloud, fuzzy cloud, because there are many ways of representing that model. Now you have new data that hasn't been annotated. I will use that model to adapt to it, meaning to actually label it automatically. So I'll put a happy face there, and I'll use it, exploit it, to label these automatically. That is what machine learning is all about. Well, at a very high level. Okay? I learn to distinguish between these two cases. There are many cases, not just two in this case. There are many different labels, and I discriminate between them. You'll understand with examples. But there are other ways of learning. Deep learning is nothing else but having this cloud a neural network. Okay? But there are other ways of representing that knowledge. It's not just a neural network. But deep learning uses a neural network to represent the information that allows it to discriminate between these. The information is just weights in these connections between the neurons. So it iterates and changes the weights so that when I activate, there's a function, the activation function that from layer to layer, it spits out what I'm expecting it to spit out. But there are other techniques of learning. One of them is what I call reinforcement learning. Remember, there's supervised, unsupervised, reinforcement learning. Reinforcement learning is also machine learning, but it's completely different in the sense that I don't give it training data that is labeled. Okay? And I'll very briefly show you what it is. What is very peculiar about deep learning, and that's why people really love it, and that's why now we have this resurgence of AI, if I increase the amount of data that I give it for training, here, all techniques, they improve, and then they reach a plateau. It's like they don't know how to interpret additional data. But deep learning keeps on learning better, and more. I mean, the accuracy becomes better and better. This is accuracy performance here. That's very peculiar about deep learning. And that's why now with a lot of data, I can get to the performance of humans. Because it gets better and better. Okay. So here are examples. They're not necessarily using deep learning, but this is machine learning. A spam detector. Not a long time ago, a few years ago, we were overwhelmed by these spams, and it was terrible. Now all these spam, not all spam, but all the email clients that you use, they have a spam detector and remove the spam for you as much as possible. And how do they do that? Knowing that some spam is good for some people, and what is good for some people may be spam for me. We're different. So the learning is observing you. How you delete emails, and how you answer emails, and how you put emails aside and don't answer it. It learns from your behavior, and it builds a model, and it knows what is spam for you. So spam detectors are using machine learning. Another application that you are using, and you don't know that actually they're using machine learning, you go to the bank, you ask for a loan, they have a machine learning model that learns from previous clients who paid back that loan and who defaulted on the loan. And what's the data they have? All the characteristics of that user who came. Whether they have a car, whether they have a house, whether they have a diploma, how many kids in the house, all that kind of information is fed to machine learning algorithm, and it builds a model. Now you come in and say, I want a loan. They put all your information and say, the probability that you'll pay your loan is this. So yes or no, I'll give you that loan. Okay. When you go and buy and use your credit card, you swipe the credit card and a transaction is sent to, information is sent to a computer that decides yes or no, I should approve that. And they learn from your purchasing behavior in the past, whether this is fraudulent or not fraudulent. So there's a prediction on how fraudulent that is, and then they'll say yes or no, I'll approve that transaction. They're using machine learning in the background. In medicine, and this is what we'll talk about next time, there are many applications to do diagnostic, prognosis, deciding which treatment to give, recommending this action or that action. So this is what we call precision medicine. Rather than dealing with everybody the same way, I create different cohorts and treat them differently despite the fact that they have the same symptoms. Here's a cool application as well that people don't think about. You have a paraplegic on a wheelchair. They can't move the wheelchair. You have to have a person moving that chair for them all the time. So instead, what we do, we have a helmet that they wear, a small hat, to get the EEG, okay, so electroencephalogram, from the brain activity when they are thinking about something. So we tell them, think about moving your left toe. They can't move the left toe, they're paraplegic, but just thinking about it, they think about sending the order, we register that activity. Then we say, think about moving your right arm. There's another activity that happens. And they do that many times, and we pass it to a machine learning algorithm, and when we distinguish between moving left arm, moving the left toe, and moving your head and sitting and whatever, different actions, different patients will have different actions because we register not the same thing, but we associate them to orders. So now when they want the chair to move left, they think about their left toe. They want to move the chair to the right, they think about their arm. They want to stop, they think about sitting. So now they can command, they can use that wheelchair without the help of anybody. They can also write, because that same movement can be done for a cursor on the screen, and then they can select the letters and they can write. So machine learning allows these people who are completely, they can't do anything, suddenly now they can be part of our society. Okay? Are we done with time? Can I
7 minutes.
7 minutes. I'll introduce what is reinforcement learning. I said that there is reinforcement learning, which is different from other machine learning. Reinforcement learning, it comes from behavioral learning. So it's like you teach a child, or you teach a dog, an animal, or how we learn in general. We try things, and what works is good, we'll do it again. What doesn't work, we won't do it again. So it's based on rewards. You ask the dog, roll. And if they roll, you give them a treat. Aha, I like getting another treat. So when they hear roll, they will roll again, they will get another treat. They try to maximize the treats that we get. And a child say, yeah, well done, you did very well, they're proud. They do something wrong, don't do that again. They get a penalty, a negative reward. And the agent does the same thing. There is the agent here, there's the environment they live in, and they do things, their actions, and they get rewards. Getting these rewards based on these actions that they do is what we call the experience. Okay? So basically you have this environment here, you have an agent, and the agent has a set of actions that it could take given the state of the world. They choose an action, and then there's an observer that says, oh, the state has changed because of your action. And by the way, here's a reward. So now the agent will do other actions with the hope of maximizing the reward that it will take. So it learns a policy of what action to do such that the sum of the rewards is maximized. Make sense? Exactly like a dog learning tricks or a human learning to behave in the world we live in. So the experience is not like, here's a bunch of annotated records and learn from that. The Experience is doing it, making mistakes, and doing good things, and you get rewards. And the pioneer in this technique is Rich Sutton. I don't know if he'll talk in this class.
Yes.
He will.
Yes, he is.
And Rich Sutton is at U of A, at the Institute. So what kind of things we can do? Patrick Pilarski will also talk after
Yes.
my talks. He'll probably talk about adaptive prosthetics. So what we do with reinforcement learning, you can teach the artificial limb to adapt to the human. Not just the human adapting to this limb, but the limb is also adapting to the human. Instead of having just a simple hook, now we have a very sophisticated limb for people who lose their arm in the military or in the farm or whatever, any other accident. And we can redirect the nerves so that they can move a nerve here, for example, that corresponds to opening the fist or closing the fist or turning or whatever. And then they learn to use this. It's not an easy thing to use these muscles to activate this other limb that they don't have anymore. And the limb is adapting to them such that now if I want to grab this object here, I'm not like a robot like you see in movies. It's more smooth and natural movement because I'm predicting, going there and predicting I'm going to grab something so my fist already starts opening, like we do naturally. Okay. So Patrick Pilarski will talk about that, and this is done with these rewards. So reinforcement learning, I try to maximize the reward, and the reward has to be defined depending upon the applications that I'm dealing with. Okay? So this is what it leads me to talk about precision medicine, and this is where I'll stop. And I want to give you a chance to ask me questions, and next time we'll talk about these applications. Yeah? Question?
How do you reward the computer? Because obviously, like
Yeah. How do you reward the computer? That's a typical question people ask me. The computer you reward it with numbers. It's like in a game. You want to be the top of the leaderboard. So it's a number, and you ask it to maximize that number.
Oh,
So it's not a treat that will taste good, and I want to eat more, like for the dog. It's not the pride, like a child you say, yeah, well done, and they're so proud. There's no emotions here. It's just a number, and if it's a bad thing that they did, it's a negative number. So when they sum it up at the end, it becomes less and less and less if it's always negative. You want to maximize it, you want to get the plus numbers. It's just, the reward is just a number, but you have to attach it to something. So for example, if I'm building a system that is filtering water, like a water treatment plant, which is a big robot cleaning the water coming from the river, and it goes to your tap. It's a sophisticated system where you have different membranes and they get clogged, and engineers are turning these different valves to change the direction of the water to clean the membranes and all that stuff. We can build it with reinforcement learning, and the reward in this case is maximizing the water going to the taps. So that application is water. And then the volume becomes number, and number that's what you feed to the system.
Yes, that makes sense.
Okay? And another application, the reward, that number, is associated to something else. It can be the money that I'm making by selling this, or the number of times people click on this application or whatever. It can be different things, but what the agent sees, this intelligent agent within the program, it's just a number. Okay? Yep. Other questions?
I do have one more, but it's 3:20 already. But is it okay if it starts?
Yes?
So with non-invasive brain medicine interfaces you mentioned, you know how you said that they use EEG to interface with the neurons that we have in our brain? So in reference to deep learning, would the neural network that the machine is using be synonymous with our neural network that we have?
No, it doesn't have to be like us. No.
So then what neural network would it use?
So there are different architectures that we build, and they have to try different architectures to see which one works the best for that particular application. Actually, in the case of this application that I mentioned was done at MIT. They were not using neural networks. They were using an SVM support vector machines. It's a completely different idea, but it's also taking training data and building a model represented in, so an SVM is basically finding a hyperplane that separates the data in space. What is this class, what is that class? So for example, you want to know, is it turning left or not? So here are the signals that, so the hyperplane cuts the space. Here's the signals that mean turn left. So it's not a neural network, but we could use neural network now, but neural network needs a lot more data. Here we don't have a lot of data because you can't ask that person to train for hours and hours and hours to say, okay, I'm moving my left toe, I'm moving my left toe. It's just too tedious. Does that answer your question?
So any other questions?
If you have other questions, you can ask me on Thursday. It's fine. And probably the questions will come up when you see examples. Like when I talked about the example of paraplegic on the chair. So I'll see you on Thursday, and thank you very much.